So with that, I would like to welcome Professor Sam Madden to the stage. He is going to be talking about programming data systems with Agentic AI. Professor Madden.
Awesome.
I'm going to squeeze behind you.
Sure. Thanks, Lori. Hey, everybody. It's good to be here. Don't clap yet. All right, so I'm going to talk a little bit about some programming, some work we've been doing on building agentic AI systems for data processing. So I'll start off just by saying, I think it's a really remarkable time to be a computer scientist or, a person who uses computers. These, LLMs and generative AI are kind of like once-in-a-lifetime new technologies, and I think it's super exciting to think about how they change the way we build all types of computer systems and applications. So I'm embracing the hype, but I'm kind of trying to do it as an engineer and think about how this changes the way that we engineer systems. And in particular, I'm interested in how we build systems that work with data. Okay, so, and I think LLMs are kind of fundamentally changing the way we do this. So I'm going to talk a little bit about that today. So the kind of vision that we have been pursuing in my research group is, can we imagine building a database system? So a database system is like, the traditional classic database system is kind of a boring thing. It takes like enterprise data stored in tables, think spreadsheets on steroids or something, and lets you ask questions over it. But it's really, the information tends to be this very structured, regular kind of information about, all the sales that happened over the last, month, or the user IDs and accounts, or all the products that you have, right? The kinds of things that we all know and love. But so I think the really exciting thing about this generative AI is that it suddenly allows you to treat all the world's data, not just the sort of information that's captured inside of these boring relational tables, as a database that you can run a query over. And so sort of by taking advantage of this amazing superpower that generative AI has given us, I think it's an opportunity to build a really exciting new class of software system, and that's what I want to talk to you about today. So the kinds of things that we're imagining is that if you're a financial data analyst, you can quickly transform all the financial documents into structured data for analysis. Or if you're a lawyer, you can search through hundreds of thousands of pages of documents to look for phrases or names or topics that are relevant to some legal discovery case. Or if you're a medical researcher, you can summarize all the data about patients with a particular disease in your hospital and compare all those findings to findings known in the medical literature. Or you're an investment banker and you can quickly correlate stock data with all the news announcements and tweets from a set of influencers you care about. Or you're an AI or a computer science researcher and you want to quickly extract the performance of all the competing AI models from all the PDFs published on the last month in arXiv, okay? So these are all things that ChatGPT or chatbots really aren't super good at. And the reason they're not super good at it is that these things require synthesis over a very large number of documents in order to be able to answer questions. And so the kind of question is, how are we going to think about going about this? And our answer to this has been to draw on actually the relational database literature. So this sort of world that research that was developed in the 1970s around essentially what we call declarative query optimization. I'll explain what we mean by that. Where we write these very succinct programs. So if you've ever written a SQL query, it's this very kind of compact way of programming over data. We want to capture that kind of succinctness of a programming language like SQL, but we want to apply it to all of the world's data, not just the data that is stored in relational tables. Okay? And so the sort of way we think about it is like the world is this database that you can query, right? And I think the sort of state of the art of LLMs, at least circa 2 years ago, was these kind of funny. It was sort of like working with them was sort of like working with some weird organism. You'd kind of probe it with a prompt and you'd get some answer back, and then you'd try something else and you'd get some slightly different answer. And it was never really clear when it was going to work and when it wasn't. And it still has it's gotten a little bit better, but it kind of still feels this way a little bit. It's pretty ad hoc and it's pretty hard to predict when something is going to work and when it's not. And so I think one of the real challenges here, and one of the things that certainly motivates us in our work, is how do we sort of develop the analog of consistency and robustness that is the backbone of enterprise data management systems, relational database systems? What's the analog of that in this new world of generative AI, where these systems are fundamentally a little bit squishy and organic-like, right? And it's further kind of complicated because natural language itself is inherently kind of imprecise. It's not really a programming language. So the way we mostly interact with these things through natural language is inherently kind of unclear whether, what the right answer might be for many of the things we ask. And then furthermore, we need to build systems that scale beyond, a few documents that you upload to OpenAI and to thousands or millions of documents you might want to process. So we have this project we've been working on called Palimpsest. Some of you may have seen a little bit about it at the workshop yesterday if you attended it. So this will be a little bit of a recap, but then I'll talk about some of the current research efforts we have to extend this system. So this is, I view it really as a preliminary effort. I'm going to show you some examples of what it can do, but it's not meant to, I don't think this is the be-all and end-all of systems for processing data with LLMs. I think it's just an example of one such system you might build. And the key idea is that it's a sort of a programming language that lets you write AI tasks in a very small amount of code, much like you might program a relational database system. And behind the scenes, just like in a relational database system, it's going to explore hundreds or actually thousands or even tens of thousands of different implementation alternatives for the program you write, and it's going to select the one that's most efficient or cheapest or fastest or has the highest overall quality. So it sort of lets you tell the system what sort of result you would like and what, whether you care about quality or performance, and then it automatically optimizes your program to find the best one. So I'll give you some examples of it operating in just a minute. I'll start with a very simple example. I'm just going to give you two very simple examples. So the first example I want to talk about is this. It's a multimodal real estate search example. So let's suppose you're trying to, buy a house in the Boston area, and you have data from some real estate website like Zillow that has a list of it has some text that describes each real estate listing and some photographs. Okay? And you have some criteria, right? You want to find a house that's in your price range, find a house that's near, say, for example, to MIT, if you work at MIT, and that satisfies some other kind of fuzzy criteria, like it's modern and attractive or it has natural sunlight. Okay? So the first two of these things are things that feel like something you might be able to do with a classic relational database, although the input to this is going to be text, not structured data. And then the last one is this kind of weird predicate that has to be evaluated over the photographs themselves in order to figure it out. Okay, so this is something that you can see why an AI model might be good to do it. And it's quite simple to write in our Palimpsest or PZ programming language. So you basically, the way that PZ works is that you declare what information you would like to extract from the data that is provided. So you say, for example, I want to have the address of the property, the listed price of the property, these other sorts of things that you want to extract. And then you point the tool at a collection of files that represent those things, and you tell it that you want to extract those columns. So effectively, think of this as creating a database now which has a set of columns attached to it, and those columns are address and price, where address and price are evaluated as the address of the property and the listed price of the property. Okay? But then you can do other things, like you can say, I want to semantically filter this data set according to the predicates. The interior is modern and attractive, and it has lots of natural sunlight. Okay? And you can also define your own filters. Like if you have some predicate, if some Python function in price range, now of course you could ask the LLM to figure out if it's in your price range, but you could have your own arbitrary code that you might want to apply to this, like in price range, you can do that as well. And then you just tell it, okay, go off and run this. And it'll give you, some answer. Okay, so there's about 14 lines of code, and note that there was no prompt writing, no hand labeling of data. Didn't really need to understand anything about the specific AI model to use this thing. And on top of that, the system is going to go automatically evaluate a whole bunch of different alternatives for doing this. And it's for this particular program, I'll show you some more results in a minute, but for this particular program, it's about 20 times faster and costs about 1/3 the cost in terms of dollar cost versus running this on GPT-4. So it evaluates a bunch of different alternative execution plans and finds ones that give better performance. Okay? So I'll just show you, I'm going to show you one other very simple demo if I can. So this is, it's kind of a silly demo, but I think it'll just, I thought it'd be fun to show you the tool. So this is imagine we've got a collection of images of animals, and we want to find the images that contain one or more dogs, and then we want to classify the breeds of the dogs. Okay, so we would write this program like this. We would extract breed from the images, and then we would say the image contains one or more dogs, and then we would run it. So I can go over here, and if this program is working, I'll just run it, and it'll do something. It's maybe a little bit hard to see this. Let's see. Hopefully this will actually run if the internet's working. Okay, so it runs, and it spits out some stuff. It says it says basically it's first filtering this, and then it's taking the it's filtering the images to find the ones that contain dogs, and then it's going to it's filtering it to find the ones that contain dogs, and then it's classifying the breeds of those images. So it's doing two separate operations here, and it takes a few seconds. We have to go off to some large language model and do this. Sorry, internet is being a little bit slow. There it goes. Okay, so, and now we can come over here. Come on, come on. Okay, we did it. Okay, so it said it spat out 3 images that matched that criteria. Oops. I don't know why it's not working. Hopefully, there we go. Okay, so you can see it said, 3 golden retriever, and poodle. Okay, so whatever this, it figured out that this was a golden retriever with the cat, this is a golden retriever, and this is a poodle, right? So it's a goofy example, but it gives you an idea of the, what happens. And underneath the covers, it actually has some plan that this shows you the plan that it came up with to execute this. So it applied a filter and then this conversion operation to get the breed out of the images. Okay. All right, so that's kind of what the basic system does, and maybe you get a feel for some of the operations. You get these semantic filters, these extractions, and there's some other data processing operations that look a lot like the kinds of things you might do in a relational database, like aggregation operations or join operations. We have support for indexing with RAGs and a bunch of other things like that. So what I want to do now is shift gears a little bit and talk about this idea of how we're sort of thinking about how agentic AI fits into this picture. So we probably all heard the buzzword agentic AI. Increasingly, the way I think of this is that you have a collection of, in an enterprise, you may have a collection of specialized agents, code modules that do certain things. And those might be very domain-specific things, like you might have an agent that knows how to go access your local database and extract some information from your that's specific to your enterprise. You might have an agent that knows how to generate code. You might have an agent that knows how to go do a lookup on some search on the internet for some piece of information. So you've got this collection of agents, and increasingly the way that we think about building AI applications is by composing these agents together. So agents are going to do things like ingest data, normalize schemas, do entity resolution, do fact validation, do some kind of like indexing of the data, or they might directly invoke some LLM. Okay, and there's of course you can probably come up with hundreds of examples of different agents you might want to provide. These are just a few examples that maybe are sort of database-like agents. So these agents, though, have kind of overlapping functionality and variable cost. Like it might be that if I want to answer a particular question, if you think about using ChatGPT or something, you could go search the internet, or you could ask ChatGPT to produce its answer directly from its own knowledge base. Or you could ask it to go search some local database. And which of those 3 strategies is the right one is probably going to depend on the specific application that you have, the specific task you're trying to execute. And those different alternatives may have different runtimes and costs, right? And so as a database person, I look at this problem and I say, this sounds like a job for a declarative database optimizer. So I want to talk a little bit about how we think about solving this problem of agentic optimization. So I'll give you a very simple example. This is, suppose you have an agent that solves problems by generating code to do this, like generates a little bit of Python code. So maybe our think of our home price example, maybe we need to extract the home price from the listing, right? And you could, of course, ask ChatGPT to go extract the home price from a listing, or you could write a little bit of Python code, or maybe ask the LLM to write a little bit of Python code to actually extract the price from the listing. Right, and why might you want to do that? Because running a little piece of Python code is going to be way, way faster than asking the LLM to invoke to running the LLM on every one of, say, 10,000 real estate listings, right? So once you generated the code, you can reuse it over and over again. But code generation isn't going to work for all problems. It's going to work when in this particular case, it's going to work pretty well because it's kind of easy to write a piece of code that uses a regular expression to find dollars inside of a real estate listing. But other things it might not work so well for, okay? And so we can ask the LLM to do this. Prices are in a specific format, so it's pretty good at this. And then the system can actually evaluate whether code generation is a good alternative or not if you can give it a few examples, or maybe ask it to use the most expensive LLM model to do this extraction, and then see if the code generation can match the performance of that most expensive model. So we can actually validate whether code generation works well. And if it does work well, then we can use it in place of invoking the LLM on every data example. All right, so you guys have probably believed me that you can get a system to do this. It works pretty well, right? We all probably, if you've played around with code generation in any of these tools, you know that it's very good at this kind of task. Okay, so what happens inside of PZ then is that we have this sort of high-level language, and the high-level language, there's a whole bunch of things that are not specified in that language, like what the underlying LLM is, how examples, all these different documents are batched together and fed to the LLM, what does the prompt specifically look like, what is the ordering in which these operations are evaluated, and then on top of that, there are also a whole bunch of different alternatives, implementation alternatives, this selection of agents that the model can do. So it can, for example, replace one of these filter or semantic filter operations with a piece of generated code. Or it might, if the data is really big, take all the documents, load them into some vector store, and index them so that when it's repeatedly reaccessing the documents, it doesn't have to go through iterate through every one of those documents every time it accesses the data with the LLM. Instead, it can directly look up relevant data from the vector store in order to be able to answer questions. Okay, so the optimizer explores this space of possible alternatives and picks the best overall plan transparently to the programmer. So you just write your program in a high-level language. It makes all these different design decisions for you and comes up with what it thinks is the best plan for doing this. So the question is, how is it going to do this? And there's kind of a key insight, which is that, remember, we're trying to run this program over thousands of documents. So the idea that we have is we'll take a sample of the documents, okay, and we'll run this. We'll evaluate a bunch of different alternatives on a sample of the documents in kind of a smart way, in order to find the plan that's going to work best for the entire corpus, right? So we're saying we'll upfront, run on 1% or a fixed number, 10 or 100 documents, figure out which plan alternatives kind of work well on those documents, and then apply that plan to the overall document set. Okay, so we're going to use an expensive. And then, furthermore, we can sort of see how well we're doing by looking at the performance of the best model. Like we take GPT-4o or GPT-4.5 or whatever it is, and we say that's the best model. We're going to compare the performance of these different plan alternatives to the best model. Or alternately, if you're know what the answer is to your problem that you've manually curated, like if you manually go extract the real estate listings that you care about and provide that as a ground truth data set, we can use that as the benchmark that we try to sort of match up in generating these plans. Okay? So I'm not going to go, I was going to show you an example of some of the plans. I won't go through the details here because I know we're trying to wrap up in about 5 minutes. But the point is there are many different alternatives that get generated by this optimization process. And these alternatives offer a sort of a spectrum of trade-off between the runtime and the quality of the answer that you get in terms of how close you are to, say, running the most expensive model or a ground truth data set that the user might provide. And so we generate these pictures that kind of look like this that show the plans generated by our system in terms of both their runtime and their dollar cost, and the cost in terms of runtime and dollar cost of an expensive model like GPT. So you can see that for this particular task, which I think is the real estate, which is the real estate search task we've been talking about, you can see that the plans have both lower runtime and higher quality than what GPT itself is able to achieve. Okay, and this is true across a whole bunch of different data sets that we've looked at. And it also is true when you compare to other systems that try to perform this task on sort of well-established benchmarks in the AI space. So there's other systems like DocETL or Lotus who try to do similar things, but we can show that we generally get lower cost and better quality than these systems. And again, I'm not going into the details here. I'm happy to provide you guys with research papers or the details about how we actually solve some of these problems. Okay, so with the time that I want to have left, I just want to talk a little bit about, it's not all roses here, right? There's a lot of challenges in building the system, and these are the things that we're really focused on in the project now. So it's challenging to think about how you evaluate cost and especially quality. Like, how do you assess whether a particular plan is a better plan than another one, right? And our answer to this thus far has been to use a small, benchmark data set that is ground truth. So if you have a ground truth data set, that's great because then you can evaluate against that. Or you might imagine using the most expensive model or taking the votes, the majority vote of a bunch of models, but it's a little bit tricky to figure this out, and that's something we're very interested in. I think another key question is trust and reliability. Like, how do you know the answers you're producing are correct? Our approach to this is generally to sort of come up with a regression or a test set. So we think of this like in software engineering. You would have a set of regression tests that you would run that would guarantee that your system didn't crash after you made some changes to the code. So the analog to that in this data space is that you have a set of answers that you believe are correct that the previous version of the system produced, and you want to verify that those answers are still the same as they were when you run a new, introduce a new agent or try out a different agent in the system. And I think this is really important, and one of the things that I think is really great about this declarative approach is that because we can abstract away from the specific underlying model, we can then guarantee that this, even if that the system will, always produce consistent answers, even, for example, as new models get introduced by, if OpenAI 4.6, comes out next week, you might be concerned that if you move to that, all of a sudden your answers would, be wrong or change, that, some system you built on top of this. And so by having this kind of test suite and by having this layer of indirection that is our programming language between the actual physical underlying model and your application, it allows you to verify that these things are true. And then there's a whole bunch of other challenges around optimizing these things, debugging them, and determining, thinking about how you select agents or thinking about when a particular agent might apply to a particular type of task that make it, kind of challenging. So these are places where we're working. So I want to just sort of summarize by saying I think this is a real victory. I think of this as a victory of this way of declarative thinking, because in this world you imagine our vision is users just say what they want in some kind of high-level language, and then under the covers the system is taking care of all the details of choosing models, crafting prompts, substituting in pre-trained models, selecting between these different agents, sequencing these complex pipelines, batching multiple things together, selecting which documents to search, building indexes for you. It's doing all this stuff under the covers that's designed to sort of take a lot of the complexity out of building these AI applications. And the net result of this is that you get better performance at comparable or better quality than you would get if you built the application by hand. So that's kind of the promise of what we're trying to do. If you'd like to read more about the system, these are the students who really are doing all the work. It's Mike Caffarella and Tim Kroska and I are the sort of faculty leads on the project. You can check out the website. This should be a link to the website. It has links to our papers. There's demos and other things there that you can go if you want to try it out. We would love to have some early testers, people who want to play with it. We're looking for real enterprise workloads, and we'd be eager to have people try it out. Okay, so with 1 minute, I want to say, like, more generally, we're really interested in thinking about how LLMs and generative AI influence the way we build data systems. We have a new initiative we're launching called Everest, where we're trying to basically, build collaborations with industry to do this. My colleague Tim Kroska will be talking on Wednesday about this, and so stay tuned. And we, again, would love to talk to you about collaborating to build enterprise applications with generative AI. So I'll just leave this slide up, and that's all I have for you. Thanks very much.